All right, good morning. Getting a bit of a late start here. Whoa, I upgraded Zoom this weekend and it looks totally different. That's a little freaky. All right, yeah, good morning. All right, I think that works. Yeah, my chat bubbles are like blue and there's like pictures next to people and dancing bears and all kinds of things. That's pretty cool. I don't normally do upgrades, but Zoom seems like it's worth it. All right, so how is everyone today? Yeah, I got the super upgrade. I got the dancing bear version. Totally. I think it's awesome that people are still into the Grateful Dead. Nice. Yeah, that gives me hope for the world. So hope everybody had a good Thanksgiving and holiday and so on. So mine was good, thank you. Um, yeah, and this is our last week of classes, so it's kind of amazing. It feels like the quarter just started, um, a few weeks ago. But we made it to week 11, so this is our last week of classes. And then next week are finals, and it's the regular final exam schedule, so it's not a final, during class this week. Regular exam schedule, so your final will be Monday at 10 o'clock, so a week from today it'll be a Canvas final. We'll talk about it more towards the end of the week. I haven't written it yet, but I'll write it in the next few days, and we'll talk about it Thursday or Friday. Um, any questions up to here on what we've been doing? Anything in the course? Anything on Bash, Unix, C, stuff like that? So the exam you have an hour and 50 minutes for. I will try to write it so that you don't need an hour and 50 minutes. I'll try to make it about, an hour 20 in length to give some wiggle room in there. Um, but it'll be similar to the midterm. You'll do a Canvas quiz, and it will be, it'll look like essay questions, and so you'll be typing in code. And again, I recommend you type your code up, outside of Canvas, and then just paste it in. Um, and yes, I'll go through this week, and for programming assignments. So let me tag this. So I'm going to make the following grade adjustments, not rgrade. Grade adjustments. Number one, your lowest programming grade will be deleted. Okay, and I'm going to set one of the assignments to just not count. So I'll set the grading to say ignore ungraded assignments, and then your lowest grade will get deleted. I'll save those beforehand just in case there's any issues that come up. But basically, one of your grades will be listed as missing, and it should not calculate that into your average. So it'll take the average of the 4 programming assignments that aren't missing. So if you got a 0, it'll turn into a missing. If you got 100 on all of them, one of them is going to go missing. But that's what that's about. The service learning project, so as we mentioned a little bit last week, we're not doing the SLP this quarter. We'll start in winter, so everybody's going to get full credit for the 5% SLP component. So those will show up as 100% sometime this week. And I think everything else in the grading is just by the book. And there's generally some sort of curving that goes on at the end. unless everybody just knocks it out of the park. Usually there's some wiggling around. I'll never change the grading curve to be worse for you. So if you look on the ngrcs.com website, it lists numeric grades, how they translate to letters. I'll never use a curve that's worse than that, right? But I may use a curve that's better than that. So, I think a C goes down to like a 73 or something. There's a good chance that will go lower, and it may be, a 65 or higher as a C or something like that. So we'll figure that out. I'm going to say try not to worry too much about grades at this point. Try to concentrate on, understanding the concepts, getting as comfortable with programming as you can, and just, working in Unix and being up to speed on the things that we've been doing for the past 2.5 months. Other questions? Yeah, again, Monday, 10 o'clock. 10 o'clock to 11:50. So see the Clark exam schedule probably for all your classes, unless you hear otherwise. Monday, 10 o'clock till 11:50 for this section. The 11 o'clock section, which I don't think anybody here is from, but the 11 o'clock section exam would be held Wednesday. So this class will be 10 o'clock to 11:50, and then the 2:15 final will be 12 o'clock to 1:50. So those are back to back if you're in 2:15 also. Please, please, please don't miss your final. It's scary for you. It's a lot of paperwork for me. So yeah, don't miss that. And similar to the midterm, it'll be primarily programming questions, but I may have more shorter questions where it's like, describe what this piece of code does or modify that piece of code to do something else or things like that, in addition to maybe a few, start to finish, write a bash script, write a C program kind of things. But I'll know more once I write it. All right, other questions? All right, let's talk a little more about processes. And again, this is not stuff that I expect you to understand it at a very deep level or anything like that. This is kind of a preview of coming attractions for other courses. So we started talking about exec and execl in particular. You may find some of these high-level concepts on the final. Like I may ask you, something about the fork command, and you should know that fork is used to clone a process, and you should probably know that it returns either a 0 or a process ID. But I'm not going to ask you to do some fancy coding, creating multiple processes and stuff like that. Cool. Alright, so I need to include uni-standard. Why do we have to include these files? Alright, why did I just put this in? It's giving me a warning, that's why. But why is it giving me a warning? What's the point of doing these includes? Other than to get rid of the warnings. So the linker can find the actual code for the function. That's essentially it. The other piece of it is, yeah, it's got the prototype for the function being used. So we're calling a function printf. There's no declaration of printf anywhere in here. How does the compiler know what to do with that? Well, because printf is declared inside standard I/O. Here's another function, execl, that's not declared inside standard I/O, but it is declared inside unistandard.h. And it's a prototype, right? We won't actually find the code for these functions inside these include files, but we'll find just the information that the compiler needs, right? You can look at these. Right, they're just sitting under /user/include, and you know it's 1,200 lines of stuff that you probably don't want to look at. But here's a declaration for, well, that's for execl, right? It says extern, which means you're not going to find the actual code for this function inside here. It's going to be defined elsewhere. It's going to return an integer, and it's going to take a character pointer. It's going to take a character pointer, and then this is something called var_args. It may have other arguments after that. And then some other stuff here, which is related to exceptions. So the code for these things is contained in what's called a library. And there are different libraries that you can link your code to. So there's a standard library that's always available when you say GCC. It'll always look in there when it's ready to link things up, and that's got printf and execl and stuff like that. There's a math library. It's called libm.a plus some other stuff in it, and it's got the actual compiled code for square roots and cosines and constants like e and stuff like that. And those things get merged in as part of the compile and link process when you say GCC. So user lib, here's a bunch of libraries sitting under here. And I believe this is the actual math library. Right, so yes, that's exactly why when you compile you have to say -m if you're going to use a math function. So what does this look like? Right, when you compile, you put this -lm that says look for something called libm. And there's environment variables that can be set up to say where should I look for these libraries, but the standard place is starting under /user/lib. And if we go down under x86 64, there's this file called libm 2.27.a. So the .a is the standard extension for these things. It's an archive file. And libm is the name, and that's the m that we're picking up when we say -lm, and 2.27 is a version number. And I think we can do AR TV, and we can see all of the compiled .o files that are inside this library, this archive. And there's a whole bunch of functions that are built in there, but you know, there's log2, there's pow. These are the long word versions. There's the hyperbolic sine function. Sorry, the inverse hyperbolic sine function. And everything that you can link to in the math library, right, is contained inside this one archive, and it's kind of like a tar file that contains a bunch of .o's, right? What are .o's? .o's are what you get when you say, you know, gcc-c sine.c. You get this object module called sine.o. And all those object modules get put together into this archive. So when you link, if I actually linked with, you know, mathera.o, signa.am.o, and this thing.o, and that thing.o, if I actually linked to all of those .o's, those would all get built into my executable. My executable file would be huge. So we don't actually link those in. We put them in an archive, and we say, hey, if you're missing anything, look in this archive. And the loader will pull things out of here as it needs them, and it will leave the rest alone. And so it ends up linking in just the things that we need. And these are pretty small, right? I mean, they're not huge. And they were, you know, all compiled at 4 in the afternoon on December 31st, 1969. Make of that what you will, but it's a time zone thing. But you know, these are just C programs. You can find the source code for these. And so how do these work? How does the computer calculate a sine or a cosine of a number? What's the C code look like for that? How does your calculator calculate a sine? Did you ever wonder about this? This is where I offer my $1 million of SpongeBob money. Yes, so someone said some sort of approximation function or series. Yes, it's a series. How do we use a series to calculate a sine of something? Taylor series, to be exact, yes. So you can use this formula to approximate a sine or a cosine. It's a polynomial. Now the ... means it goes on forever, but you know, by the time you get out to, you know, x to the 101st divided by 101 factorial, you're talking about a really small number, right? So you only have to carry this out a few terms to get a pretty good approximation. And if you're doing single precision calculation, you don't have to carry it out too far. If you're doing double precision, you need to go out a little further. But it's really not that far before you've got a pretty dang good approximation. And so sines and cosines and other trig functions and logarithms and exponentials, those are calculated mostly using polynomials. So you can write a C program that basically just, you know, calculates these terms, adds and subtracts them inside a loop, you know, that does the first 15 terms or so, and bingo, you got your sine or cosine. Alright, and I'll mention one more trick because everybody should know this at some point. Suppose you need to calculate, you know, ax to the fourth plus bx cubed plus cx squared plus dx plus e. Well, to calculate x to the fourth times a, that's like 5 multiplications, that's 4 multiplications, that's 3, that's 2. Well, actually, that's 4, 3, 2, 1, 0. So it looks like 10 multiplications you have to do in here plus 5 additions, right? Which would be a lot of work, especially for, you know, a 15th degree polynomial. There's a trick you can use to calculate polynomials like this, and it does not require you to store all of these powers of x ahead of time, because, you know, when we calculate x to the fourth, we calculate x cubed on the way, right? And we could, you know, store that somewhere and stuff. But there's a trick we can use, which let's see if I can pull this up. Right, we can write this polynomial like this, and if you multiply it out, right, this piece right here is ax squared plus bx, and then if you add c, and you take all that and multiply by x, you get ax cubed plus bx squared plus cx, and you can add d. And when you multiply that by x, you get ax to the fourth plus bx cubed plus cx squared plus dx, and you can add e. What's nice about writing it out like this, though, is what do? You do a multiply and add, a multiply and add, a multiply and add, a multiply and an add. That's 4 multiplies and 4 adds, and you're done. And you can build hardware to do this, right? So some of the complex instruction set machines, things like the VAX, had single instructions you could call to evaluate a polynomial, and it was coded into the hardware, right? Why? Because anytime you want to do something with math, you're going to be using one of these series to calculate, you know, a floating point value, a sine, a cosine, something like that. And if you can make that 10% faster, right, your customers' programs may run 10% faster. All right, let's pop our stack. So how the heck did we get to talking about libraries? Oh, I was asking you why we include things. Okay, so so presumably we know why we include things now. All right, so that's why we have to put in this uni standard, right? It's prototyping the execl function. All right. So ready to call execl. We're going to call execl, give it arguments of bin date, and then we're going to print out done. And we played with this last week. Right, so that compiles fine now, and if we run it, it says ready to call execl, it shows us the date, and then it exits. And the interesting thing here is that it never prints out this done command. All right, so this is where we left off on Friday. And the punchline here was that this execl function basically replaces the current running process with the code of this function, this file. Right, so execl will open up this file, read the executable code, all of the execution information out of that file, and then load it into itself. And your process becomes a fundamentally new process. So fork is used to create a clone of the current process. That's how you make a new process, but that new process is doing exactly the same thing as the process that created it. So once you have that clone process, now you have to get it to do something different. That's where you use exec for. Right, and it basically overwrites the essence of that process so that when this returns, it's no longer about to execute this printf statement. right? When it returns, it is /bin/date, and that program is now beginning to execute. So how do they say it? Replaces the current process image with a new process image. Yeah, that's basically it. But lots of details, and you can put in, for example, argument lists that you want to pass to this new process that's being created, right? That's how we pass argc, argv. And the function should not return, right? It only returns if for some reason it fails to create this new process. Because the notion of returning is part of this old process, and once exec executes, this is no longer what's being run. All right, and where is this used? This is used, on my command prompt. When I say date, right, it prints out date. How does that happen? Well, bash gets cloned with a fork, so now you have two bash processes running, and this clone does an exec on wherever data is stored. Well, it looks in the path and it sees should look in /bin, and it checks /bin and it finds a date, so now it says exec /bin/date, and the code for exec opens up that executable program, pulls the executable code out, loads it into itself, and now we have our original bash process, but the clone process is now executing date. It was cloned, but in a way where its standard out was the same as the original process's standard out. So when date runs and it prints out the date time information to standard out, it goes to the same standard out as our original process. That's why we see it here. And if you do BC, right, it sends its output to the same standard out, but its standard in has been connected to the same standard in of my original bash process, which is why I can sit here and I can type something like 2 + 2, and that goes into this entirely new process that's running BC. And if I look, there's two processes running right now. There's bash and there's BC. And then when I exit BC by a Control-D, for example, that process goes away and bash is still there and it's still listening to standard in and so on. Right? So this is how everything happens inside Linux. And we can use this to do our own, process creation and manipulation. But this is really the thing that's happening, every time that you run a command from a bash shell. All right, so the other thing I wanted to talk about was pipes. And pipes are this technique that we can use to communicate between processes. So I'm not going to worry about exec for a bit. I'm just going to go back to looking at forks. So let's make a clone of the process. So if my process ID from the fork command was 0, I'm going to call a function called child. And child's going to do all the stuff that we want the child process to do. Otherwise, if I get to this line of code, I know that I'm the parent. So I'll just print some messages. All right, so let's just start off with something that does nothing. We'll just make a clone, and we'll either be the parent or the child. Let me do this clean. nothing too exciting there, right? We ran this, and there's a parent and there's a child, and they'll usually come in that order. They could come in a different order. There we go. So there, the child happened to get to its print message before the parent did, right? They're two separate processes. They're running asynchronously. What warning? I didn't see any warnings. All right, so let's do some communication between these two. So let's make a conduit. For communicating between parent and child. Okay. So we're going to use the command pipe. All right. So pipe takes one argument, which is an array of two integers, and it will fill in the values of those two elements of the array with information we can use to send messages from one end of this pipe to the other. So I'm just going to do the following. I'll call them FD for file descriptors. So we'll make the pipe. Let's look at what pipe returns to us. All right, so we'll see what this file descriptor is that comes back. That looked funny to me. All right, so FD is an argument to the pipe function. All right, so let's run this, and it's not terribly exciting, right? The two arguments that got, the two values that got filled into our array were just 3 and 4. And that's going to be consistent every time we run this. All right, so what are 3 and 4? Remember, we normally have 3 streams that we can use for doing input and output. Standard in, which is what we read everything from. That's got an ID number of 0. Standard out is stream 1. Standard error is 2. Well, we're creating 2 new streams, 2 new things that we can use to send information in or out of. In this case, file descriptor 0 and file descriptor 1. And it's just going sequentially. And if we called pipe again, the next 2 values that got used would be 5 and 6. They're just indexes into some big, gory internal data structure that the system knows about for keeping track of input and output, right? And remember, ultimately, you know, there's nothing magical going on here. When you send something through a pipe and have something reading from the other side of it, right? There's nothing actually being moved around. It's just memory locations. It's just data. It's 1s and 0s. But it's being interpreted, you know, when I place these values into these memory locations, it's being interpreted as saying this goes into this pipeline, and then this process, when it reads from this other file descriptor, it says, well, let's see what's been placed in those memory locations, right? So this is all, you know, abstraction layers. All right, so we've got a pipeline created, and the way we can think of this is, you know, as a pipe, and we write into one end and we read out of the other end. These pipes are unidirectional, okay, so stuff only flows in one direction. And this is the input side, and this is the output side. And when we call pipe FD, where FD is a 2-element array of integers, right? The pipe function fills in a value here. That's the file descriptor that we can use, the index we can use for writing into the pipe. And when we want to read from the pipe, we can read from whatever value was loaded in FD bracket 1. Alright, so the nice thing about this is, when we say fork and we create a clone of our current process, it clones the entire process. And since we're calling the pipe function up here and we're loading particular values into the elements of this array, both processes, the parent and the child, will have access to that information. The parent and the child will both see the same values for FD bracket 0 and FD bracket 1. And so that's a common basis that we can use for communication. Alright, so I'm the parent. Let's write a message to the child. Alright, so we're going to use another type of I/O here. We're going to use what's called the write function and the read function. Okay, so this is low-level stuff. This is what things like printf use to actually send their output somewhere. They make calls to write. And so write takes 3 arguments. Takes a file descriptor, 0, 1, 2, 3, 4. Takes a character pointer, and then something that says how many characters we want to write. Alright, so let's send a message to the child. So we're going to write into wherever FD bracket 0 says we should write, which we know is going to be a 3, but we're going to use FD bracket 0. We'll send the string hello followed by a new line, and then we have to say how many bytes we want to send. And I only have to send 6 bytes to get hello new line, but I also want to send the null terminator. Okay, otherwise I have no way of knowing how long my string was that I sent. So I would actually do string length of hello new line plus 1, but I'm just going to count them up. HELLO new line null terminator. Let's send 7 bytes. Alright, on the child side, let's read something from the parent. And so reading looks exactly like writing. We read from, in this case, file descriptor 1, right? Because that's where stuff should be available that's been put into the pipe. So we'll read from FD bracket 1. We'll put in a character array because we don't know what those characters are going to be, and we'll put in the length of the character array. So I'm going to have to make a string here which says 120 characters are available in this array called buffer. And I'm going to save the result from the read function itself, the return value. And the return value is the number of bytes that were read. If the pipeline has closed, if I hit end of file, then read will return a 0. And I think it'll return negative if there's an error. Yeah, if there's an error, it'll return negative. Otherwise, it tells me how many bytes were read. All right, so we'll read from the pipeline, and then let's print some stuff out. So we'll print that out. And let's just print out character by character. We'll print out I, and we'll print out buffer bracket I. And that's the end of our child process. All right, so we've got a main program. It's forking into two processes. The parent process will print a message for us to know it's the parent, and then it will use the write command to write 7 characters, 7 bytes into the writable end of the pipe, and then it will, return an exit. And the child will tell us it's the child. It'll read from the parent. It will call read and read whatever is available on the read end of the pipe, up to 120 characters. It'll tell us how many characters it actually read, show us that number, and then we'll go through and we'll print out the characters. This will either work or it'll cause my laptop to burst into flames. Alright, so FD is undeclared, right? Because I declared FD in main. And I really needed to have it available inside my parent and my child process. So how do I make FD available? There's 2 answers. One of them's a really good answer. One of them's a really not as excellent answer. That's the not as excellent answer, but it is a way to do it. And in some cases, that would be exactly what you would want to do. Just make this global because you want everybody to have access to it. But there is a way we can be a little more nuanced about it. So what's the other way we could do this? We could declare it inside the other functions, but we could also pass it to the other functions. And sometimes that makes sense, sometimes not. Now, if nobody was watching, I might just make this global. And in fact, when we get to Java and we start working with objects, we're really going to be using global variables. We're just not going to call them that. But we could be a little more subtle about this and just pass this as an argument to these functions. And now, it's defined inside here, it's scoped inside here, but we're making it available where it needs to be used. So yeah, let's declare this inside here. And I could do int fd bracket 2, or I could do int star fd. And either of those should work. I don't think it makes any difference which way you do it. But you do have to prototype your functions accordingly. So let me just do an int star fd. And I could have called this anything I wanted, right? It's just a local variable name, but I'm just going to stick to calling it fd. So now when I try to use fd bracket 1, it should pick it up from the argument that was passed. Alright, so no more errors. And let's see. Alright, so parent and child read from the parent, and read returned -1. So something went wrong, which often happens. I think what went wrong was I got these backwards when I wrote this down. So this is the input side, which means we want to read from that. We are just about out of time. Let's see if I can make this work on the second try. Hey, that's better. All right, so this should be fd bracket 1 that you're writing into, right? So let me label these differently. There's always this problem when you're talking about two sides of communication. The question is, whose perspective are you looking from? right? So from the perspective of somebody who is writing into this pipe, right? This is the input end of the pipe. This is the output end of the pipe. But let's look at the other perspective, right? Standard in is what we read from, right? It's the keyboard, it's the file that we're redirecting from, and so on. The input side of this pipe is the side that we're going to read from, right? It's the side we're taking stuff out of, which is this end over here. So FD0 is on this side, that's where we read. The output end of that pipe, standard out, that's what you're writing to. Well, this is the end that you write into, right? So from the perspective of the pipe, this is the input. But from the perspective of the process itself, this is the output end, right? This is where we put our output to. So write into FD1, read from FD0, right? Write into FD1 and read from FD0. And so the parent wrote into the pipe, and the child said it was reading from the parent. Read returned 7. There's the 7 bytes that it read from the pipe. HELLO, character 10 is a new line, and character 0 is the end of string terminator. Yeah, sorry, that does add a new level of complexity. And it you know, clearly trips people up even after they've been doing this for a long time. But it's quicker to recover from the more that you do it. So when I first tried doing this stuff, right, it was like infinitely confusing, and took a lot of fiddling. But you know, if you get them backwards, you figure it out pretty quickly and you switch them around. All right, so that's a basic pipe setup. We'll talk a little more about that tomorrow. I'm not going to go too much deeper than that, although I will make a few comments tomorrow. What would happen if the child was run before the parent? It will hang out there and it'll wait for the parent to do its thing. That's a really good question, though. So, you know, let's have the parent sleep for a bit. So there's the child, it's reading from the parent, but there's nothing in the pipe yet. But the pipe is not closed. So eventually the parent writes some stuff in, and then the child's read returns, and it sees the characters. Alright, so we'll play with this a little more tomorrow. Have a good afternoon. I will see you next time. Thanks.